this Max tutorial, we're going to create a rolling 3D spectrum. Before we start, what are we trying to do? First, we're going to use a pfft tilde object to create a spectrum and turn it into a matrix. Then we're going to use jit.gen and a feedback loop to create a scrolling spectrum out of this matrix. And then we will use the spectrum to draw lines on screen using a jit.gl.mesh object. I will start with a jit.world object and a jit.p window. And let's begin by creating our pfft. pfft needs another patcher that is stored separately. So let's quickly do this. Let's just call this one spectrum to matrix, and I will save this in the same folder that our main patcher is in. Then I can close this. Then we can create our pfft. As the first argument, we need the name of the subpatcher, which is spectrum to matrix. And the FFT size, let's do 512 for now. Okay. Opening this up. Okay, this seems to be fine. Okay, what we now need is an FFT in. This will give us our real input and our imaginary input. Then we need a car2pole tilde object in order to turn the real and the imaginary into our amplitude and our phase. But for what we're doing, we will only need the amplitude. And now we can use a jit.poke object to poke these values into a matrix. But before we do that, let's first create our matrix. Let's call this one spec for spectrum. And then we can say jit poke spec. And in the first inlet, we're getting the signal value. And in the second inlet, we will get the bin index, which is then corresponding to the position within the matrix. Okay, that's all we need to do in our pfft. I'm going to save this, close this. Okay. In order for this to work, let's first initialize this. So we need one plane. This needs to be float 32. And then we need half of the pfft size. These bins will go from 0 to the sampling rate, but we only need them from 0 to the Nyquist frequency, which is half the sampling rate. So if we have a sampling rate of 48,000 hertz, this would go from 0 to 48,000, but we only want it to go from 0 to 24, because everything above that will just be mirrored. Okay, I just saw this mistake here. Then let's create a jit bang to bang this on every frame, and another jit.p window so we can see what's coming out here. At the moment, nothing is coming out of here because first we need to feed some audio in here. I will use arguably the best sound file in Max, Zhongli. And then maybe I have to reinitialize this. Okay, now you can see that we're getting something in here. Okay, this leads us then to the second part, which is the scrolling matrix. So as you can see, this is just 256 by 1. So essentially we have only one pixel row on the y-axis. And now I want to create a bigger matrix and scroll and take this first pixel row and scroll it down across the whole matrix. In order to do this, let's create another matrix. This will have 3 planes, also float 32, 256, and let's say 150 for now, and a depth 0. So 150 means that we will have 150 rows or pixel rows on the y-axis. Okay, I will put this somewhere here. So in order to get this scrolling effect, we need a feedback loop. In order to do this, I will create a jit.gen. Let's call this one feedback. And then, yeah, maybe do something like this. And then we can duplicate this. This will be the second input. And we can create our loop like this. So this matrix is coming in here, then it gets processed, coming out here, getting back in here. Now, what is this processing we need to do? So first thing we need to do is we just want to take the first row of pixels. In order to do this, we can use the cell object and say, okay, if this cell, first we need to take the y component. So if the y component of our cell is exactly 0, we know that this will be the first row at the top. Let's just quickly check this. Maybe let's copy this one. Okay, now you can see we're only outputting the top row. Okay. And then I want to, so if we are in the first row, I want to take the new input from the spectrum. And if we're at any other row, I want to take the feedback that's coming in. So we can use this operator here, which is checking this. And so this is the condition to test. If it's true, we want this input, and if it's false, we want input 2. Let's quickly look at this. Now we can see that we're only getting this in on the first row, but nothing is happening here because everything else will be just black. So in order to scroll or drag this across the screen, we're going to use the nearest operator at bound mode clamp to sample the feedback that's coming in. But I want to sample it not at the exact position, but I want to always look at the next row. So if we're at row 2, we will look at row 1 and set row 2 to row 1, and then in the next iteration, row 3 will become row 2, and then row 4 will become row 2, and so on until this whole thing is scrolling down. Okay, in order to create this offset, first we need our normalized coordinates ranging from 0 to 1. And then we need to subtract exactly 1 row of pixels. So in order to get 1 row of pixels, we can use this expression object and say output 1 equals 1 divided by the dimensions of y. And we only need it for y, so let's create a vector that leaves x alone and only takes y. Okay, let's see if this works. Ah, yeah, now you can see that each row of pixels that is bigger than 0 or bigger than the first one will, for each frame, look at the previous one and set itself to those values. And I mean, this is already working. The problem that we have here is that this is highly frame rate dependent. So if I'm using a Q metro, so if the frame rate drops for some reason, so if we have a frame rate like this, oh, of course this needs to go here. Okay, now I got it. So if we have a frame rate that is very slow, the scrolling will also be very slow. And if we have a frame rate that is very fast, the scrolling will be very fast. So I want to do something that is frame rate independent. So in order to do this, I will take the delta time between frames into account. I made a whole video about this technique. I will put it into the description of this one. In order to do this, we need to create a parameter called this one delta. And let's first check what this might be. So we're in the ballpark. So we can use jit.time at mode delta, and this will give us the time difference between frames. So this is 0.02 approximately. So let's set this here. So 0.02. And then I will use the inverse of that as my speed variable, which should be 0.0250. So what we can do now is we can multiply this by our delta time, so difference between frames, and then by our speed. To be back where we were. Then I will create a dummy inlet for them. Yeah, let's maybe do it like that. Okay, first we're inputting the delta, and then we can input the speed. So this is 50 for now. If we increase the speed, this will also increase. If we slow it down, this will also slow down. Okay. This looks great. And now the scrolling speed is independent of our frame rate. Okay, that was a lot. Coming to the next and final part. Now we're going to draw lines on screen with that. In order to do this, I will first create a jit.gl.mesh at draw mode lines. Yeah, that's it for now. And then we need another jit.gen. Let's call this one, what do we call it? So we have the position, we have the scale, and we will also change the color. So let's call it that. Okay, so output 1 is position, output 2 is color then. Okay, what do we need now? First, let's first draw the line grid on screen. So I'm using signed normalized coordinates for that. Maybe I can already connect this one here. But I don't want to draw it like that. I want to like turn it 90 degrees. So in order to do this, I will get the Y component and the X component. Then I will create a new vector. So the Y component of this vector will be the height, which will be determined by the incoming spectrum. And Y and X will just be the flat plane. Okay, we don't see anything anymore. I will just create a camera. Let's say look at 0, 0, 0. Then yeah, also set tripod and look at 1, and then for the position, I think I want it to be a bit tilted, so let's do something like this. Oh yeah, something like that. Okay. So now we can see it again. Okay, so what we want to change now is the height of those lines. And maybe if we take a closer look, you can see that those lines are not connected yet. So the way these are connected is 0.0 to 0.1, 0.2 to 0.3, 0.4 to 0.5, 6 to 7, 8 to 9, and so on. So in order to also connect the lines that are in between that, we can use jit.multiplex and create another jit.gen, call this one multiplex. And what we will do in here is essentially the first outlet will just be the points that are coming in. And the second outlet will be the points shifted by 1. So in order to do this, we can say nearest pix this time. So this one doesn't take normalized coordinates, but the exact cell coordinates. Bound mode clamp, and then we can sample the input we're getting here by the cell position plus the offset of one cell on the x-axis. Okay, then we can put this in here. Now you can see they're all connected to the center because this second inlet is essentially set to 0, and now they're all connected. Okay, then sorry for this short digression. Then to continue, we can now use input 1 in order to modulate the Y position. First, I want to normalize this, so I will take a quick peek at the values that we're getting in. So cell block, start this off. Okay, this is way too fast. This tells me nothing. So let's say jit3m, and this will give me the maximum. Okay, this is the maximum. This is the mean. Okay, this seems a bit high to me. Yeah, let's just experiment with that. So let's divide this by something like 10. And then clip it between 0 and 1. So we'll be sure to get a number between 0 and 1. And then we can add this in here, but we don't want to add it to all the components. We only want to add it to the Y component. So we can patch this in here for the Y component. And now we can see the spectrum is doing something. But you can see that there's an emphasis on the lower frequency. Most of the energy is happening down here. So what we could do now, because this is already in a range of 0 to 1. I mean, we could increase this here. Let's take a look at the values that are coming out of this. Looking into the second plane. Okay, this looks about right. Yeah, what we could do is, in order to emphasize the lower values, we can use a power function, or let's use fast power, something like 0.5. Or yeah, this looks good. Then we can also create the color. So for the color, we also need this multiplex thing I built. We can plug this in here for the color input. So this just turned black because we're not getting any color yet. So what we could do is we could use the HSL to RGB function, and then put in a vector here, 0.5, 0.5. And as an input, so we could control the brightness by what is coming out of here. And then we could use normalized coordinates to create a gradient for the hue. So in order to do this, we just take the X component. So ranging from 0 to 1 on the X-axis. Then we can say something like mix 0.2, 0.8. Okay. I don't like how that looks, so maybe let's also use a fast power in between. And I think the yellow should be the higher frequencies, and the bluish, at least for me, makes more sense to be at the lower frequencies. So let's reverse this. Okay. Still not too happy with those colors here. Yeah, maybe something like that. And we could also clip the color or the brightness that's coming in here. So let's say clip 033, 066. Okay, this looks okay-ish, I would say. What we could do to make this look a bit cooler is we could use a jit.gl pass and at fx name, what was it called? Bloom HQ, I think. And then change the bloom amount, change the threshold. What else do we need? Maybe the exposure bias. Where is it? Okay. Okay, this is way too much. Yeah, maybe it would look better if we also set blend enable 1 and then blend color add. Okay, I like this more. And we also need smooth shading in order to interpolate between the different colors. Smooth shading 1. Okay. Okay, we're getting there, we're getting there. Okay, then we can say transform attributes to arguments, and then this is set. And now you can see that the spectrum is very spiky. What we could do to filter this a bit is we could use a jit slide and then say, I don't know, slide up something like 5, slide down something like, let's try 10. And then you can see that this is the spectrum is way smoother now. Okay, a final thing I would like to change is, so as you probably know, FFT bins are linearly spaced in hertz. So the octave from 100 hertz to 200 hertz is only obviously 100 hertz and contains very few bins. But an octave from, let's say, 5000 hertz to 10,000 hertz covers 5000 hertz and contains many more bins. You could say that low frequencies have fewer FFT pins per octave and high frequencies have a lot more FFT pins per octave. But for the human pitch perception, the octaves are much more important than the actual frequencies in hertz. Essentially what I'm trying to say is I want to put an emphasis on what is happening down here. In order to do this, I will create another jit.gen, and I think this will be the last thing for this tutorial. Let's call this one log sampling. I mean, we're not really creating a logarithmic scale, but so essentially what I want to do is when we're looking into our normalized coordinates and we're only taking the x component, I want to stretch this part so we have an emphasis on the lower frequencies. And in order to do this, we can again use this power function. And now you can see we have an emphasis here. And in order to apply this to the spectrum that's coming in, we can just use this to sample. So we can say nearest, and again, bound mode should be clamp. And then we're creating essentially new UV coordinates. So this will be the X component. And for the Y component, we can just take the Y components from the input. And now, and also maybe a thing that I didn't do up until now is, let's maybe also listen to what we're doing here. Because I guess it's always a good idea to listen to audio visualizations. Okay. Yeah, now you can see if we compare the input to the output that the lower frequency content is stretched. But let's put this in here. Yeah. What we also could do is, okay, we have 512. So if I'm having a sampling rate of 44,100 divided by 512. So one frequency bin is 86 Hertz. And if I'm multiplying this by 256, yeah, of course, Nyquist frequency, but we could also use 128 and we would be at 11,000 Hertz, and I don't think there is much energy above 11,000 anyways, so if we change those numbers here, maybe it looks even better. Yeah, I like this a lot more. Then here we can change the scrolling speed. And what also looks very cool is if I'm stopping, you can still see this wave of audio rolling. Another thing we could do, so now if we take a look at it, the lines are connected horizontally, but if I'm changing the multiplexing to this, they will be connected in the Z direction. So whatever you prefer. So if we prefer one of them, it can be changed in here. Yeah. Okay, I think that's it for this tutorial. I hope you got something out of this. Thank you for watching.